Da-da-da, we gotta do quantum stuff now. Max Planck's quantum hypothesis. Okay, so Max Planck, German physicist. We're gonna get into some of his weird ideas at the time of how physics works. One of the things during this era, though, of like early 1900s, middle 1800s, was astronomers were doing some really weird stuff at this point in time. Okay, stuff that like they just weren't expecting. So astronomers had observed something that is referred to as a black body spectrum. So astronomers have a black body spectrum. And what they mean by this is a black body absorber or emitter is a specific type of object. What a black body spectrum absorber or emitter represents is an object that would either absorb or emit all of the radiation either falling upon it or that it's giving off. So like 100% of the energy is grabbed or 100% of the energy is given off. Nothing is lost on a black body. Okay? These black body spectrums that they created, or that they were seeing, they could in general kind of plot what was going on there, but they weren't exactly sure at the time of what was causing it or how to do this mathematically. They knew what they saw, but they didn't have the math to back it up, which is kind of a classical thing in the world of physics. We see something, and now we need to prove it. So what we now know is that for a black body radiator, we can check the luminosity output or the energy output of a black body radiator from E sigma A t to the fourth. We've actually seen this equation previously in this class. We briefly talked about it in thermodynamics when we had the three different types of energy transfer: conduction, convection, and radiation. For a black body system, this emissivity here is just given a 1. Everything is emitted out into space. That sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8. A is the surface area of this radiator, something like a star, so that's 4/3 pi r cubed. And then T is a temperature to the fourth. Naturally, it's in Kelvin. If you have no idea what we're talking about on this, go back and check out that old video. So with this right here, there's actually one interesting thing we can do with this. If we make a graph of the intensity of stars or of light based off of their wavelength, which would mean that frequency, since their inverses, goes the other direction, we'd actually see that we could create a graph where colors like green would be on the left and colors like orange would kind of peak a little bit further to the right. And as we get even more red, these colors peak further and further to the right. And I kind of drew that orange one a little bit wrong. Let me redraw that. It's really the green one that messed it all up. Sometimes drawing is difficult. But as you see here, these peaks are at different locations. You can quickly find the peak wavelength for a star because the peak wavelength multiplied by the temperature of that star will be equal to 2.9 times 10 to the minus 3. And this is a little weird. This is meters Kelvin. Meters Kelvin. Not millikelvin, meters Kelvin. Which simply means if you know the temperature of a star, 2.9 times 10 to the minus 3 divided by that temperature in Kelvin gives you the peak wavelength. This is an approximation, but it's a very good approximation for blackbody radiators. Tom just asked the question here, can these graphs not overlap? What these graphs here are representing is a normalized luminosity output. So notice here, this, I kind of drew this wrong. It looks better if I don't draw it. Generally speaking, these red and orange graphs are going to be lower, but they're going to be broader. Where this green graph, it's going to peak higher and then kind of come down more shallow. So in terms of the question, can they overlap? That's really these graphs are like 3 different stars here. Okay? Because these would each be their own peak wavelength. Okay? So maybe this green star is, or this star that's outputting at a green wavelength, maybe it's just a much more luminous star. Maybe it has a much larger surface area on it, meaning it's physically larger. So with this, we can actually take Planck's equation and we can actually expand this just a little bit more. We're just going to take it to one step further. We're going to say the energy at some point n, and we'll come back and talk about this in a later video, will equal some n h nu, or f if you're using that, whatever. We'll see how energy levels come into play with this equation a little bit later on. Now, this is wild, because while Planck was able to create this constant and set up this equation, we still have to remember, this was not the norm. The norm was to think that energy is a continuous quantity, and it should not be quantized or broken up into these parts. It should not have to have this constant here, which dictates that I need to go in these steps. It's not going to be until years after Planck that some really brilliant, amazing physicists come along and take this idea and blow it out of the water, winning Nobel Prizes and setting up their futures for the history books. We're talking about Einstein. We'll see that in some later videos. But for now, this is finished. Until then, adios and take it easy.